I am going to talk about phase diagram of polymer blend and polymer solution based on the experimental result. And the experimental idea is there is a LCST and the UCST, which is a lower critical solution transition temperature, and the other one is upper critical solution transition temperature. So let me start with something that I said before, theoretical. Phase diagram. Okay, always like to use the convenience of the defining the chi versus. I guess you can say it as a volume fraction. So let's just say I would just say just to be consistent with, we'll just say pi a, and then you will see that this one has a phase separation. And for the symmetric case, this has been the 0.5 when NA is NB is same as N. So just for keeping for the simplest idea for the polymer blend. And this one was essentially chi critical was 2 over N. So that was the data for that. And you have a phase separation so I will just put a shaded area once more. So this is where you have a phase separation. So this is where you have two phases, which is A reach and the B reach. I mean, as you can see that when you are as a chi goes up, for example, at this position, you have this and that. That will be pi a prime, which is higher than higher in B content. This is a pi a double prime, which is another phase that has a more A, because pi a volume fraction of an A is more higher than 0.5. So this is where we have two phases, where the down here in the white area you don't have phase separation. But now this one is going to putting into a task. Now the experiment people study the phase diagram. The way that you can control the interaction is by changing the temperature. Okay, so this is a little crooked. So let me just delete that. Okay, so this is a region. Okay, so here now the problem is changed now into the temperatures. In some cases, you will see the phase separation happening this way, and sometimes you will see the phase separation in this way. So obviously, the way that when the phase separation occurs, this is where the phase separation occurs in two phases. Sometimes this is a phase separation occurs to two phases. And in the previous my discussion, I gave this pretty much very simple idea about chi interaction parameter depends on the temperature. So pretty much the most kind of simple idea for now is chi is inversely proportional to temperature. Okay, so that's a pretty much the good idea. So, but what that means is over here, when you increase the temperature, your chi value is going down. Okay, for this idea, and that's only true when your B value is positive, but that's usually the case. So this is a case where when the temperature goes up, your chi value is coming down. So which is a opposite of your theoretical phase diagram. So this is what you see here, and then this is a behavior we call UCST, upper critical solution transition temperature. Okay, so this temperature is called the TUCST. Okay, so that's where. So if, as long as you heat it up, essentially this is more like the case where you have a solution that polymer blend that is non-miscible, or polymer solution that is miscible. By heating it up, eventually you will make things more miscible there. Okay, so think about doing this kind of heating. This is a heating. You heat up the one and then forcing them to be miscible, and that's when you do the UCS behavior. Wherever there is a temperature increases, sometimes actually chi values can go up. This is a little not normal, but it's quite well observed in the case for the polymer blends. Okay, and so this is one is an opposite. So this is what we call this behavior is a LCST, lower critical solution transition temperature. Right? So then this is a TLCST. Okay, so in this case, you have actually things are miscible. Okay, so let me probably put a different colors. So you have things are miscible, but now you're heating it up. Eventually, they will be immiscible, right? So miscible at low temperature, you became immiscible. At high temperature, and then that's the case for the essentially LCST, whereas a UCST is a one that on heating it becomes miscible. Okay? So this is a phase diagram that is shown up in the textbook, and essentially it summarizes pretty much same behavior. In some cases, you are seeing this single phase window. Some of the cases actually, let me just draw this one more time to summarize what this figures means. It is rare, but it is sometimes there are figures that showing this. This is like a UCST, and then sometimes they're going to LCST, and they can have. So therefore, what that means is, in the lower temperature, things are non-miscible. When you heat it up, they are miscible, but when you heat it further, they'll phase separate again. Okay, this is a very complicated scenario where this people have seen this. Right? So this is a say pi A, and this is a miscibility. So this is a single phase window. This is a single phase, whereas you have a phase separation at low temperature and high temperatures. Okay, and I also mentioned before this is a thermodynamically meaningful line. That's what is known as a binodal, and the one inside with the phase separation window, there is something called the spinodal lines. Whether it's LCST or UCST, okay, both you see these regions, and both regions are essentially kind of shaded in a same way to be consistent, to show where the phase separation occurs. Within the phase separation should occur with within the binodal line. So this is essentially thermodynamic criteria for the phase separation or not. So that's a more meaningful. However, the line that's showing as a spinodal line is a dotted line, right? This spinodal line, and this is essentially phase separation stability. So there is a concept about the phase separation stability criteria. stability criteria. Stability criteria. Okay, and so whether things are actually metastable or not is a very essentially based on the local stabilities. So the one within this, okay, this is what in this figure also says metastable regions. So metastable region is things are locally the phase separation is not favored because of the metastability. The only way they can do the phase separation is nucleation and growth. Whereas those are inside of this spinodal line, which is, let me probably put a different colors. So let me just to recolor them. So within the yellow one, the one is shown as a pink, right? This is where essentially is not metastable. And it didn't say in this textbook, essentially this is an unstable region. Okay, so it's not, so therefore the phase separation happens very fast by what I call the spinodal decomposition. And if you search the word of the spinodal decomposition, there's a lot of documents there, and you can have a look at it. If you guys need it, I can explain further in my regular classroom sessions. But this is a way that I will just leave it that way. So what I have shown you to you here is where the previous section I just talked about phase diagram using this parameter composition versus a measure of essentially the repulsion, dislikeness. And this is where the phase diagram should occur. And then in the experiment, you want to relate this, the theoretical interaction parameter is something that you can control in a lab using the temperature. So now using the temperature as an axis, and people discover the phase separation depending on the temperature changes. And the common one is this is increasing the temperature, you are making things miscible. That's upper critical solution transition temperature. Low critical is an opposite of upper critical, which is making things phase separate upon heating. And in some kind of the uncommon cases, and then you can see this, something looks like that, and that's the third case is where you are seeing the phase separation happens at low temperature, at the high temperature at the same time. That cannot be explained simply by this behavior, and then people have seen this. So now there is a more different versions of theoretical model than simply using the Flory-Huggins model. The beauty of Flory-Huggins model is their simplicity of the equation, but now some people are trying to modify the equation of Flory-Huggins by either changing the chi expressions or changing the way that how entropy is written and how enthalpy interaction is written, expanding from the regular solution theory. I think that will be a good subjects for this. For this one, is actually one of the famous example is polystyrene in acetone. That's the one that actually having miscible, non-miscible. If you heat it up, now polystyrene becomes a soluble in acetone. If you heat it further, actually you will see the things are phase separating. And so let me try to give you the actual example of the data. And then this is the first thing is actually experiment. Result in the first one is a polymer solution. If you remember the polymer solution phase diagram that I introduced from the previous YouTube videos, it is skewed. towards a lower concentration of polymer, unlike polymer blend, which is more like symmetric. And the first example is polystyrene cyclohexane. This is where the Flory has done a lot of experiments. So this is polystyrene in cyclohexane. The other one is polyisobutylene in diisobutyl ketone. And these are the system, I think that partially because of the polymer can be synthesized with a more or less well-defined molecular weight so that they can study this, the phase separation. And let me just give you the same kind of shaded one. So if you see here, this is where the experiment result was observed. Phase separation at a lower temperature, and then the higher, when you heat it up, the phase separation goes away and things are being miscible. And this one is particularly for 43,600 gram per mole polystyrene. Okay, so what do you see here? This is a UCST. And then experimental-wise, just like a critical chi, this is what we call the critical temperature. So critical temperature, now you can see, let me put a little different shading of the one by, for example, using the 250 higher molecular weight, phase separation persists even up to, let me just kind of ignore the other molecular weight. This is overlap, but the whole idea is phase separation, the temperature is went up to a higher temperature. This is the critical temperature. Okay, so that's an example here. And from here, actually, you turns out to be find an important discovery. One is critical solution transition temperature, whether it's an upper UCST behavior for this polystyrene cyclohexane, is depending on the molecular weight, right? The high molecular weight goes up, the critical solution transition temperature that is go up. And this is something that you will find out. And the second one that I didn't talk about in detail, but this is, you can see that in the limit of molecular weight goes to infinity, right? You can see this from this data. This is a molecular weight. As the molecular weight goes up, the critical solution transition temperatures are going up like this. And so the critical solution rate goes to temperature where in the limit of m goes infinity, and then this is 1.3 million. That's a pretty high molecular weight, and has been known as a theta temperature. So this is one way to define the theta temperature. And as you know, the polystyrene in cyclohexane, the theta temperature is 34 degrees C. And this is what has been discussed, introduced before when I talked about osmotic pressure in the light scattering experiment. So where is your theta temperature? Is about right here. Okay, that is your theta temperature. And then that's the one that I just shown up, as an example. So this is another aspect about looking at polymer phase separation in solution or blend. And you can look at the critical temperatures, dependence on the molecular weight, and then the Flory-Huggins theory actually also define where essentially when the molecular weight goes up, and this is where you can find yourself for that. Okay, and this is the same thing, right? So when you're having a high molecular weight, you will have phase separation up to a much higher temperatures. And when you are having a lower temperatures, lower molecular weight, the phase separation has happened in different ways, right? So with a lower critical solution temperature. So this is a lower molecular weight, and the one is up there is a high molecular weight. And then you saw the dotted line. That's a measure of, once again, this is a spinodal. and this is a binodal lines. And within the pocket of binodal line, you will see the phase separation within this polymer solution, which means the polymer became insoluble, right? So that's what this means. And like I said, the polymer solution is there is a case, and this is a case, a more complicated phase diagram, and this is a PS in acetone. Okay, so when you have a polystyrene, which is almost like with a benzene side group in acetone. Acetone looks like this. So nail polish remover, that's an acetone. And now you see here is a lot more involved. And then this is a high molecular weight, and the molecular weight is about 10,000 and above. You see the phase separation here. So let me give you the idea about this. Right? So that's okay. So that's where the phase separation occurs when you have a molecular weight of 10,000, which is not so much high molecular weight, and the one in between is essentially pockets of window where the miscibility is for here. So, in this diagram, you should see that for molecular weight of polystyrene, which is a 10,300 gram per mole, things are miscible, polymers are soluble in acetone. Based on this experiment, at the temperature window 0 degrees C and the higher, and then let's say 150 degrees C or something. So they are miscible. They are miscible within that window. Okay, so this is a rather and you can imagine that doing the acetone has a boiling point. So to push this experiment to a higher temperature, you have to seal the solution under, I guess, a visually clear test tube, sealing it, and you can heat it up. You can essentially acetone stay as a liquid up to temperature higher than boiling point because they can evaporate, and you can push that to see the actual phase separation eventually occurs at the temperature higher than 150 degrees C, then you will see that happen. So these are the people who has done that experiment for that. But now, this is the case. So this is a case, okay, well, I'll see this is a UCST and the LCST at the same time. And for the case for when your molecular weight is a little higher, which is 19,800 gram per mole, in this case now the situation is a lot more, in a way, simplified. So if you see this, the higher you go, the two-phase window, this is an LCST, the UCST two phases and higher molecular weight. This is a LCST two-phase regions at for the molecular weight of 1900. Eventually, what do they happen? This two-phase window, they kind of meet together, right? So it's almost like a meeting the LCST and UCST at the same time. And then this is where there are two phases immiscible, right? So in this case, PS is not soluble in acetone for entire temperature window. It's not soluble. So if you have your acetone, you're trying to dissolving it, it's not possible. when within this kind of the composition window, right? So this is a composition window. Let's say a volume fraction of polystyrene is between, I'm just eyeballing it, just let's say about like a 7% to 20%. Right? So if you're trying to make the solution of polymer, let's say 10%, we are 15%, you cannot possibly have making things more homogeneous. But if you actually by making this polymer solution at 5%, right? So this is how you actually, one of the training that you should have. If you have a polymer solution at 5%, and then if you kind of make it go up, yes, you can. It's possible for you to have a single phases right there, but if you have, let's say, 15%, it will be two phases throughout, right? So it's not possible for you to dissolving it. So this one shows that polymer can be possible. You can make it not soluble or make it soluble, and because this is a one phase here. Oh, I don't like this. This is a one phase on this kind of hourglass like phase diagram, and within this is a single phase, one phase, and miscible. So if you, however, right, if you make, for example, if you make polystyrene 5%, there is a miscible temperature window exists. Okay, so that's a one way to look at this. But as you can see that sometimes you'll see this UCST and LCST exists separately like this, and then it's a this temperature is, what do we say? There the critical solution temperature is a molecular weight dependent, and the people has done a different experiment diagram. This is done in the experiment 1972. And I look at the more recent one, and then this is the one that I mentioned to you that polymer blends are miscible, and then the example was polystyrene blend with polyvinyl methyl ether. So this is the one, vinyl methyl ether. This is an academic interest that a lot of studies, because this one known as LCST. They can phase separate at the higher temperature. So here I am going to show shading the area. This is a temperature, and this is where you are seeing these two phases. You see this? So this is where you are seeing the phase separation, and the dotted line is experiment. The dots are experiment dot points, and the lines and dotted lines are theoretical kind of fitting to that one. And this is a work by the Julia Huggins and the Jane Easton. Jane Easton is she's a theoretician at the Dartmouth colleges. And but now the reason that I'm showing is okay, this is an LCST for the polymer blend of polystyrene and PVME. That's for sure. But I want to show you the difference between the deuterated polystyrene, polyvinyl methyl ether, versus just regular hydrogenated polystyrene. We just call it polystyrene, that's the one, and PVME. So deuterated polystyrene means you have a CD2CD, and here is all deuterated. Okay? People are, deuteration technique can be used to kind of color the polymers chemically very similar to the identical one, and then the people can see that, right? Can see how the behavior, and there's advantages for coloring this by the deuteration. Okay. Okay, so here. This paper is actually quite about regular polystyrene versus deuterated polystyrene phase separation blend. And you look at this, the area, I'm here highlighting this line, this region, which is experimental data points, and Jane Ibsen is a theoretician trying to understand this diagram. So there are two data point sets, which is the dots. The one that matches with this two-phase window with LCST behavior, this is the one that is shown as a hydrogenated polystyrene, which is a regular polystyrene. But upon the deuteration, your LCST changes to a higher temperature. So this is let's say about 400 K. Now this is moving up to 440. So 40 degrees C increase in the LCS temperature because you change from the hydrogenated polystyrene to the deuterated polystyrene, right? So CH bond versus CD bond, there's a different polarity differences. And then when you have a large molecular weight, those interaction parameter essentially manifests itself to a higher numbers, and then you are seeing the essentially different interaction as a polymer, although the discrepancy in the interaction or polarity difference between CD versus CH bond is different, so that then people can see this the difference in deuterated polystyrene PBME blend forming LCST, hydrogenated polystyrene with a PBME, polyvinyl methyl ether polymers. So this LCST can, depending on either whether things are on the, I want to show this. First thing is an LCST. The second one is depending on deuteration and hydrogenation. They can also be affected, the critical LCST temperatures. So as a person doing the experiment, this is the one essentially temperature for LCST. And this is the temperature for TLCST. Okay, so people study that using the blend. And for this one, certainly the critical temperature depends on the molecular weight. So they have to define the molecular weight here, which is 190,000. That's a sufficiently large molecular weight. Okay, so that's probably, before I move on to the block of polymer chapter, this is a quite elaborate one. Thing that I have introduced about experiment result on the phase diagram. First thing is a polymer solution, and second one is polymer blend. Okay, so polymer blend, most likely that the polymer blend, actually this is an LCST is shown up. When you look at here, and these two examples only show the UCST, and this is much more well known. When you're trying to dissolve the polymer, it's not dissolving it. If you're heating up, there's a chance that you can reduce the chi value by heating it up, and then this one you might be able to dissolving it. So that's why even polyethylene that is not easy to be dissolved, you heat it up in the high temperature, you can make a homogeneous solution, single phase, and then now you are in quote-unquote business, so that you can perform the gel permeation chromatography experiment when polymers are well dissolved as an individual chain, and you can separate polymer chain based on their molecular weight sizes. Right? But when you're having this is a scientific interest that when, for example, this is a case where polystyrene is dissolved in acetone, the phase life behavior is a lot more complicated. And they can show both LCST and UCST, and also some intermediate window. You have a more like an hourglass of two phases window. It's almost like LCST and UCST meet each other at the halfway. And if you further increase the molecular weight, it's simply you have a two phase. Your polymer cannot be dissolved in the acetone. The typical polystyrene that you produce in a commercial scale, their weight average molecular weight is in the ranges about 250,000 grams per mole. So if you have a regular polystyrene chips or polystyrene cup trying to dissolve in the acetone, you cannot dissolve in it. Okay, but they can still swell it somewhat, And so that's something that because of the, if you go to the lower concentration, they should be, still can form the, trying to dissolve it somehow. Okay, so this miscibility not only depends on temperature or the, but also the concentration ranges where you are in.